So these last two sections, E and F, have a lot in common because it's really about how these monosaccharides link together to form what we call disaccharides or polysaccharides. And so I am going to start with disaccharides. And I already defined this earlier for you, that it's two monosaccharides connected by a covalent bond. The bond that actually connects them is what we call an acetyl group, okay? And so these are two monosaccharides connected by an acetyl bond. And remember, in order to form an acetyl, what you have to do is you have to take a hemiacetyl plus, well, in order to get to an acetyl, another alcohol. Okay, you should know that. So a hemiacetyl is an aldehyde or ketone reacting with an alcohol. Once you have that hemiacetyl group, which you do when you form a ring, you react another one with an alcohol and you form an acetyl group. Now, the first one I want you to know, the first monosaccharide, or excuse me, disaccharide, is what we call maltose. And I'm going to start this on its own page. Okay, so maltose is a, you can think of it as a breakdown product of starch. Okay, you've heard of malt before, and it is 2 glucose connected by, and this is what I want you to know, what's called an alpha 1,4 linkage. Okay, and this is the acetyl bond that's actually formed when these two things come together, acetyl. Okay, so one of the things I think that's good to be able to draw, like I said, is alpha. Because this is an alpha bond, I'm going to draw alpha D glucose. Remember, alpha means down. So you should be pretty proficient in drawing this now by your memory. And I'm going to draw another one next to it. Now, the one next to it, it doesn't matter if it's alpha or not because it's not involved in the bond. It could be a squiggly line here. I'll just make it alpha. Okay, now, remember, alpha 1,4. So, this is carbon number 1 on this glucose. This is carbon number 4 on this glucose. And that's what comes together to form, this is a hemiacetyl on this side. And this is the alcohol. And the way we draw this is we draw the ring, we draw the oxygen out, and this is kind of the, without all the distraction of all this other stuff, this is what we call the alpha 1,4 linkage. Okay, and I'll put the OH here. Remember, I can put a squiggly line if it doesn't matter. You could keep it down if you wanted. I just want you to know that it doesn't matter, because that can actually open and close still. That hemiacetyl is still open. So this is what we call maltose. Okay, so you should know 2 glucose connected by an alpha 1,4 linkage and a breakdown product of starch. Okay, another name for this acetyl group, by the way, is what we call a glycosidic bond, and it's just another term that is used for this. Okay, so that's the first one I want you to know, maltose. That's the disaccharide. And then you're going to see that when we get to starch, it's connected by the same type of bond. Okay. Another one is called cellobiose. And this is similar thing. It's, you notice I said a breakdown product of starch. This is a breakdown product of cellulose, which is a polysaccharide. You'll see that in the end of this video. And this is actually 2 glucose connected by a beta 1,4 linkage. So same thing, I'm going to take glucose and I'm going to start with it, but it's going to be in the beta structure this time. So the one on the left is going to be beta. The one on the right, it doesn't actually matter, but I will draw it in the beta just so we can see it. Okay. And so if you think about the way this is going to link together, this is carbon 1 and this is carbon 4, this whole glucose molecule sort of has to shift up. And so the way this looks is like that. Okay, that's with all the other stuff out of the way. This is a beta 1,4 linkage. Okay, then I can put everything else in, down, up, down, for the glucose on the left. And this would be down, up, and that one's already connected. And then, as you can imagine, this could be either or. It could open and close in a disaccharide. When we get to cellulose or polysaccharide, it just keeps building up and up and up. Okay? So you probably know this, but humans can eat maltose. They cannot eat cellobiose. Okay? So we can't eat cellulose. That's, I mean, we can eat it with sort of fiber, but we just don't, we can't break it down. Okay? So humans can eat maltose. So interestingly, if you think about it, humans can break the alpha 1,4 bond between glucose, but it can't a beta 1,4 bond. Okay. The next one I want you to know is what we call lactose. You've heard of that before. And this is another name for milk sugar, right? And it is a beta D glucose, or excuse me, beta D galactose plus glucose. Okay, and it's a disaccharide, and it's connected by a beta 1,4 linkage. You should know that. So I'm just going to draw this together because this really looks just like cellobiose. Okay, so if you think about this, I've always been sort of amazed by this, that the galactose, the only difference, remember, glucose is down, up, and then down, but galactose is up on carbon number 4. If you went back, that's the only difference. This is carbon 4 for galactose. And this is always on the left, so that matters. It's galactose. And then the glucose is over here. And this wouldn't matter which one, the one on the right, but down, up, and down. And that's the beta 1,4 linkage right there, because that's carbon number 1, that's carbon number 4, this is the beta 1,4 linkage. So if you were to go back and look at the difference between this molecule and cellobiose, it's that this one OH is pointing up, and humans can drink this and eat this, but we can't if that OH is down. So if you ever think to yourself, why do we have to know anything about chiral carbons? Well, one chiral carbon turns a molecule into something indigestible than lactose. That's kind of interesting. And you know, you've probably heard of someone that's lactose intolerant. When you have lactose intolerance, it's because you actually aren't making the enzyme that breaks down this bond, okay? So it's an enzyme called lactase, and it breaks the beta 1,4 linkage. And we all have it when we're children, like when we're newborns, because we can drink milk. And then as we get older, most people become lactose intolerant because they stop making this enzyme lactase. And there are many people who can still drink it as an adult. Just the most of the people in the world can't. Okay, so because they stop expressing that. All right, and then the last one I want you to know is what's called sucrose, and then I'm going to show you some images. And this, as you know, is table sugar. So, and this is, the difference for this is, this matters. This is alpha D glucose and beta D fructose. Okay. Now this is sort of a unique looking molecule. It's actually connected by what we would call a alpha beta 1,2 linkage. And I'm going to draw it over here because it's kind of an interesting thing. If you think of glucose, so I'm going to draw glucose first, and it's alpha. So I'm going to come back to that. Up, down, then an OH like this. And alpha means down, and I'm going to kind of draw a big line here because I'm going to connect it to the fructose, and it's a 5-membered ring, and it's the opposite one that I drew earlier in this lecture, or in this section. And this is the fructose here, and this is the glucose, and you can see they're attached by their hemiacetal and hemiketal groups that connect like that. So it's kind of an interesting looking structure. You do not have to know how to draw it, but I do want you to know the linkage. Okay, I want you to know the linkage, and I want you to know which monosaccharides are involved in it, and that it's table sugar. But you don't have to be able to draw it. You should be able to draw the others though, because they're very common structures. So, and things that you have to know. So if you look, here's a couple slides that you can see. This is maltose, malt sugar. Okay, we can eat this. This is cellobiose. Here's lactose, so you can see the only difference between lactose and cellobiose is this 1OH here. See, it's down here. It's up here. It's the same thing though. And that's sucrose or table sugar. You can see the linkage here. All right. So let's finish this section up by talking about polysaccharides. So this is F, polysaccharides. Now, there are 4 distinguishing characteristics that I want you to be able to define, how to define a polysaccharide. So 4 distinguishing characteristics of polysaccharides. Now, the first one has to do with the type of monosaccharide. And the monosaccharide, you can have like one type, which we call like we would call that a homopolysaccharide, or 2 types. You can have multiple, but 1 or 2 different monosaccharides. All right, all the ones we're going to talk about are one single type of monosaccharide. The second thing is the length of the chain. The third is the bonds or slash linkages. And the fourth is whether or not they have branching or not. Okay? So the 3 different types that I want you to know are all made of glucose. They're all many glucose molecules connected in their different usage. And obviously these are going to we're getting such big molecules that we can't draw them. We can just know the characteristics, and I can show you some images of them. So the first one I want you to know is starch. And you should know that this is a storage of glucose polysaccharide in plants. And starch can actually be broken down into 2 different types. It can be broken down in what's called amylose and amylopectin. Okay. Now, amylose, you don't have to know, but about 15% of all starch is amylose, and about 85% is amylopectin. Okay. So the only difference between these have roughly about 300 to 500 glucose units. Okay, remember polysaccharide, many of these. And they have alpha 1,4 linkages, okay, just like maltose. And there's no branching. Okay, so that takes care of the 4 characteristics. One type of monosaccharide, how many, 3 to 500, the type of linkages, and there's no branching. And then this can actually have up to amylopectin, up to 100,000 units, glucose units. And it also has alpha 1,4 linkages, but it also has alpha 1,6 branches. Okay, and so let me show you an image of this. This is an image of just a single continuous chain, and these are branching points, but I want to show you the actual chemistry. That's if you had an alpha 1,4 and an alpha 1,4 and an alpha 1,4, so this would be amylose. Okay, amylose can kind of form these kind of neat spirals that form. That's the way it packs. But if you have amylopectin, you can see it. There's this 1,6 linkage, so that one carbon that's outside the ring can actually go and form another bond, another acetyl bond between the carbon of another one, and then these branches can take place, and that's what it looks like. Okay? So that is what starch is made up of. Now, I also want you to know what is called glycogen. And this is glucose storage in animals. Okay? And this is really just like amylopectin, but it can have up to 1 million glucose units, and there is more branching. Okay, so it would look basically just like this structure that we had in that image. It's just there'd be more branching, and I think it's important for you to understand why there's more branching. So I guess the question is why? Well, when there's more branching, there's more points that you can knock off glucose. So there's more removal points. And you know that animals have to be able to break down glycogen so that they can escape from predators. And so we can actually access our glucose faster, our glucose reserves, because of all these extra points, and so more removal or retrieval points so that we can break it down faster. And plants don't need to do that. Plants don't need to escape. They're rooted, right? So same thing. If you want to make 1,4 and alpha 1,6 linkages for the branches, okay? And then the last one I want you to know is what's called cellulose. And cellulose is a structural polysaccharide in plants. And it has beta 1,4 linkages between glucose molecules. And it actually has no branching. Now, what's interesting about this is we probably all think of this as fiber. And if you look at the image of this from your book, you can see this is cellulose. And one of the things it is important for is for fiber. I'm going to show you some others. But you can see it kind of forms this kind of like linear line that goes up and up and up. And what happens is, I'm going to draw kind of a cartoon of this. You can get these glucose units that go up with these beta-1,4 linkages. And then another bundle will go right next to it. Okay. And then another one. And these can actually pack in to one another, and they form this water insoluble packing or package kind of type structure. And if you've ever torn a blade of grass or tried to break a stick, and there's those kind of, it feels like those lines of that you're tearing, that's actually cellulose kind of all packaged next to one another. And so you can tear it, you can break it along one of these lines right here, but it's actually pretty hard. It's, wood fiber can be used in buildings for hundreds of years, and trees can last for hundreds of years, thousands of years. And so it's really a strong structure. But it has this beta-1,4 linkage that we, obviously, humans can't eat. But it is an important part of a fibrous diet. So with that, I'm going to stop this